Now, refraction of light. So you know what is refraction of light. This is a next phenomenon exhibited by the light when light bends at the interface of two media. When the light passes through the interface of two media, it will actually changes the direction, it bends. So this bending of light at the interface of two media is known as the refraction of light. So you have seen so many realistic example about the refraction of light. So it is written here, you can see, let us consider the case of a apparent displacement of the pencil partly immersed in the water. You can see it is bending at the interface of the air water interface. So these are the example, and you just go through it, you will get several examples about the refraction of light. Other examples like if a coin is placed at the bottom of the glass which is filled with the water, you can see the image of the coin is just somehow uplifted, and the apparent distance, apparent depth of the coin will be lesser. So these also one example of refraction of light. So this is the refraction through a rectangular glass slab. So just go through it. Activity, this is 10.10, and just follow the figure and then you will understand. So this is ABCD, actually the glass slab we have taken, and you know the surrounding of this media, that is the glass slab, it will be air. So here two media we have taken, that is air and the glass. So when light will fall on this surface, that is AB surface, then you know this is normal. N dash is the normal. It falls on this AB surface, makes an angle I1, and after refraction the angle will be R1. You can see here the air is the lighter medium and glass is the denser medium. So when light falls, just going from the rarer medium to denser medium, then the refracted ray always bends towards the normal. So actually you can see, if glass is not present there, absent of glass, it will follow this path. Actually it has been bent, the refracted ray has been bent towards the normal. You can see this is the normal, n dash is the normal. So that is R1. So we can see from this figure R1 is less than I1, and again then it will follow the same path falls on this interface of two media again, and now this media interface of two media is nothing but glass air interface. You can see it is going from denser to rarer medium. Then what will happen? So in this position the ray will go away from the normal. You can see as it is lighter, then it will go away from the normal. Then the R2 angle must be greater with respect to I2. So after all, if we see the figure, this ray, EFO ray, and this O dash H ray, what happens actually? The line, the directions of the ray has not been changed. Direction is same, but you know there is a lateral displacement has been occurred. So in the absence of the glass slab, the ray will follow this path. You can see here this dotted line is here. So it will follow this path. But the presence of the glass slab, it has been followed this path. So what we conclude? So we can conclude from here. So there is a lateral displacement has been occurred for the case of a, you can see here what is written, refraction through a rectangular glass slab. Okay, you have understood. Now this is actually the law of refraction. It is written here, the incident ray, the refracted ray, and the normal to the interface of the two transparent media at the point of incidence all lie in the same plane. So it is actually the same with respect to the reflection formula. But the second thing is very important for the case of the laws of refraction. The ratio of sine of angle of incidence to the sine of angle of refraction is constant. So it is very important. So what is sine? Sine is nothing but an operator. So if we just apply this operator with respect to I angle, that is the incident angle, same thing, it is the refraction angle, and we will take the operator, sine operator with R. Then sin I by sin R. This is the ratio. This is written here. The ratio of the sine of angle of incidence and the sine of angle of refraction is a constant. You can see here written constant for the light of the given color and for the given pair of media. So it is constant when there is a condition. So it is very important. You must remember, for the light of given color. For a given color it is constant. So actually what is the meaning? Actually this meaning is that for a particular color and particular pair of media. So you have taken air glass interface or other glass air interface or air water interface or water air interface. If this thing is constant, so you have not altered the pair of media and you have not also altered the color, then sin I by sin R always be constant. So this is very important. So this constant, actually finally we have understood, this is nothing but the refractive index. So you can see we learn about refractive index. So what is refractive index? So this constant value is called the refractive index of the second media with respect to the first. So this is the refractive index of second media. Suppose I is the angle of incidence, the ray falls on the air and finally goes to the water. So this is nothing but the constant. This is the refractive index of water, because water is here the second media. And now the refractive index. So what is refractive index? So refractive index is nothing but the measurement of bending of light, how much it has been bent. So you'll get an idea from this refractive index. And refractive index has two type of refractive index are there. One is actually called the absolute refractive index and other is called the relative refractive index. So relative refractive index is that, so if you just find out the refractive index of any media with respect to the other except air, then it will be relative refractive index. So if the one medium is air, then absolute refractive index will be applied. Okay, now from this figure you can see this is medium 1, that is air, and this is medium 2, that is glass. So light is coming from the air media and falls on the glass media, and then refraction will occur. So here what is the refractive index? So refractive index you have to write in this way. This is a symbol of writing refractive index, N21. That is the refractive index of 2. So always you have to take the second media. So N2 means it is a refractive index of second media, and beside it is written 1. That means the ray is coming from 1. So instead of that you can write in this way 1 N2. So in front of a prefix you can write 1. So 1 N2, then the similar meaning will be there. So 1 N2 means light is coming from first media going to second media. And then what will be the measurement of the refractive index? So speed of the light in medium 1, speed of the light in medium 1 and speed of the light in the medium 2. So V1 by V2. So what will be N1? N1 means refractive index of the first media. Then the with respect to second media, you can see this path will be retraced. Then speed of the light in the second media with the speed of the light in the first media. So V2 by V1. Just it will be reciprocal. And this is speed of the light of the air. You can see it is nothing the second media. You know 1 to 2 suffix are given here, but here given one suffix. You know. So that means first media is somehow air. So that's why it is not given here instead of 0. So we always put 0 nm. So we have not written here. So this speed of the light in air. So that is C, and speed of the light in the medium, that is V. So this is nothing but the refractive index of any particular medium. So it is coming from that medium. So this is the second medium. So second medium speed is given in the below, and speed of the light in the air will be upper side of the fraction. So this is absolute refractive index. You can see. So if you compare any two media, if you write refractive index with respect to one media to other media and except the air, this will always be relative refractive index. But if one medium is air, then it will be absolute refractive index. You can see here. So some typical data are given here. Refractive index, these are the material, and refractive index is given here. If you don't want to remember these things, note from the table 10.3 that in optically denser medium may not possess greater mass density. For example, kerosene having higher refractive index is optically denser than water. So actually optical density is not similar with the mass density, that is we call density is equal to mass by volume. So that density is not here we are talking about. Here the density, that is optical density. Optical density is somehow different from the mass density. And now the refraction by spherical lenses, you know that this is a convex lens, and convex lens is a converging lens. So it will converge at a point, it is second focus. Obviously for the lens there are two focus, f1 and f2, because light can fall on left hand side also and right hand side also, but the two sides can be used. And here this is the case for a concave lens. You can see if parallel rays falls on the concave lens, it will actually the divergent lens we know, and it will the rays will be diverges, and if we just extrapolate the rays, actually it will seems to meet at focus. So always image will be formed for virtual. So now go to the cases. For the different cases, image formation by lenses, very important. You can see these tabular form already we have read for the concave mirror. So there is a very good relationship in between the concave mirror and convex lens. Just remind, this is the 6 cases. Already these 6 cases we have read about, and this is very similar with respect to the concave mirror 6 cases. You can see here infinity at focus, beyond 2f1, between f2 and 2f2. So here changes are here, changes has been made only for 2f2. You can see at the case of the concave mirror we have written C, that is the center of curvature. Okay, here center of curvature has been replaced with 2f2. Only these changes has been occurred here. Other all the things are exactly similar. So we will not read all these things. Image formation by lenses using ray diagram. Parallel rays passing through f2, it will be divergent and it seems to come from f1. This is the passing through f1. After refraction it will be parallel to the principal axis. It is actually seems to pass through f2, but actually after refraction it will passing parallel with respect to the principal axis, and it will be undeviated. If the rays heading to the optical center, it will be undeviated. It will be the same for both the cases. If it is heading to the principal optical center, it will be undeviated. And here all the cases, if object is placed in infinity, image will be formed at f2. Object is beyond 2f1, image is formed between f2 and 2f2. You know this formula. And 2f1, it will be also 2f2, that means similar distance from the convex lens. Here in between f1 and 2f1, then it will be beyond 2f2. You can see here. And this is the, if object is placed on f1, image will be formed at infinity. You can see these two rays will be parallel. So if it is parallel, they will meet at infinity. That's why image will be formed at infinity. And here you can see this is a special case for the convex lens. If object is placed in between the optical center and focus, image will be formed at the same side, but it will be erect, virtual, and highly magnified. And these are the cases for the convex lens. Convex lenses, two cases are there for infinity and remaining all the positions for the object from infinity to the optical center, it will be same. The image will be formed that is erect, smaller, virtual and erect, and smaller than the object size. And sign convention, already we have used the sign convention. Same sign convention already we have discussed. Now the magnification will be h dash by h1 and it will be equal to v by u. In the case of the concave mirror, in the case of the mirror, you have seen this one minus v by u. but here it will be only V by U. And finally, the power of the lens. What is the power of the lens? Actually, you know, this lens is a convergent lens and concave lens is a divergent lens. So it will diverge the rays, it will not meet actually. But for the case of a convex lenses, but it merges after refraction, it will merge the rays very close to the optical center. That means it has the ability to merge it faster, merge it very close to it. Then it has the power, it has more power with respect to the second one. So this can be identified, this can be used by reciprocal of focal length. So if focal length is very less, then power will be greater. You can see here, and it is denoted by Phi, and the unit will be diopter. You can written here, it is written diopter, dioptres, diopter. So it is 1 diopter is equal to 1 meter to meter inverse. So go through it. If there is a problem, then comment it in the comment section of the YouTube video. Thank you for watching my video. If you think video is helpful to you, don't forget to hit the like button and subscribe my channel for next upcoming videos. Thank you.